Okay, new chapter is direct current DC circuit. So first of all, for the DC circuit, this is a symbol for the battery. This terminal is positive, this is negative. When two or more batteries are connected in series, negative is connected with the positive and the voltage is added. But when batteries are connected in parallel, then positive must be connected with the positive and the negative must be connected with the negative. So positive, positive, negative, negative, and here the voltage remains same in parallel. But the current becomes double. Now, this is a fixed resistor. This is a variable resistor. This is also a variable resistor, but called rheostat. Now, this is the symbol for another resistor, which is called light dependent resistor. This is another resistor. It is called thermistor. Now, this is the symbol for the voltmeter. This is the symbol for the ammeter. This is the symbol for the galvanometer. And this is the symbol for the ohm meter. And this is the symbol for the capacitor. This is a symbol for diode. And this symbol is LED. So fixed resistor, variable resistor, but it is also called the rheostat. This is LDR. This is thermistor. This is voltmeter, ammeter, galvanometer, ohm meter, capacitor, diode, and LED. Now resistors in different combinations. Number one, parallel combination of resistors. For example, we have number of resistors like 1, 2, 3. So these resistors are connected parallel to each other, and this is called junction. So this is another junction. So this P and Q are junction. If the wires are drawn like this, it means they are not connected. They are just crossing over each other. But when this cross is marked here with a dark dot, then this is a junction, mean they are connected here. So this is P junction, this is Q junction. Now, the current, mean the electric traffic, when enters the junction, then current leaves the junction, suppose I1, I2, and I3. And in previous lectures, we have done that in parallel, voltage remains same and the current divides according to Ohm's law. V is equal to IR. When voltage is constant in parallel, then the current is inversely proportional to resistance. Mean the larger resistance, suppose R1 is the largest one resistance, then the current I1 will be the smallest. Now, sum of the currents, sum of currents means sum of electric currents entering the junction is exactly equal to sum of currents leaving the junction. For example, at P, I current is the entering current, I1, I2, I3 are the leaving current. So we can write I entering is exactly equal to sum of leaving I1, I2, I3, and this is called Kirchhoffs first law. So the Kirchhoff first law is sum of the currents entering the junction is equal to sum of the currents leaving the junction. If entering current is represented by the positive sign and leaving current is represented by the negative sign, then the equation becomes I minus I1 minus I2 minus I3 is equal to 0, mean total current at the junction is 0, mean the resultant current at the junction is 0. So the current entering exactly equal to leaving. No current is staying back at the junction. So the total current at the junction is 0. So this is the Kirchhoff first law. So I is equal to I1, I2, I3. But do remember, there is no delay between entering and delay between entering and leaving the junction. Okay, so there is no delay between entering and leaving the junction. Now the current I is equal to Q divided by T. So we can write Q divided by T is equal to Q1 divided by T1, Q2 divided by T2, Q3 divided by T3 instead of I1, I2, I3, and I, because I is equal to Q by T. Now, entering, leaving current, time same. So T1, T2, T3 will not be different. They will be the same. So this equation can be written as Q divided by T, Q1 divided by T, Q2 divided by T, Q3 divided by T. So Q divided by T is equal to 1 over T common, Q1, Q2, Q3. So T cancel. So the total charge is equal to Q1 plus Q2 plus Q3. Hence, charges are conserved. Total charge entering is equal to the sum of the charges dividing at the junction. So the Kirchhoff first law is also called law of conservation of charges. Now, according to Ohm's law, V is equal to IR, and I can be replaced with V over R. So the Kirchhoff first law equation, I is equal to I1 plus I2 plus I3, can be written as V over R, V over R1, V over R2, V over R3, because V in parallel remains same. So V over R1, V over R2, V over R3. So V over R V is taken common, 1 over R1, 1 over R2, 1 over R3. This V cancelled. So the resistance, mean the reciprocal of the resistance, 1 over R1, 1 over R2, 1 over R3, and so on. So this is the journal formula to calculate the total resistance when the resistors are connected in parallel. Thus, this formula shows that total resistance in parallel decreases. For example, 3 resistors are connected in parallel. One is 5 ohm, second suppose 10 ohm, third 15 ohm. So 1 over R, 1 over 5, 1 over 10, 1 over 15. So the LCM is 15, LCM is 30, not 15, 30. So 5 6 10 3 15 2 So this 1 over R becomes 9 plus 2, mean 11, divided by 30. So the resistance becomes 30 by 11, which is 2.7 ohm. Look, this 2.7 is smaller than 5, smaller than 10, and smaller than 15. Hence, in parallel, total resistance is smaller than the smallest resistance even. So in parallel, total resistance decreases. But when only two, do remember, I'm saying only two resistors are connected, R1, R2, then we can write a formula, the total resistance, the product of two resistors divided by sum of the two resistor. This is valid only for the two resistors in parallel, not for 3, not for 4. Look, suppose this is 6 ohm, this is 3 ohm, then the total resistance will be product divided by sum. So 18 divided by 9, 2 ohm. When this is calculated by the journal formula, 1 over 6, 1 over 3, LCM is 6, 1 plus 2, so 1 over R, 3 by 6, so R is equal to 6 by 3, and same answer. Now the resistors are connected in series combination. Suppose this is first resistor, this is second resistor, third resistor, just one track, R1, R2, R3. So the electric traffic, mean the current will remain same because there is no branch circuit. But while passing through each resistor, voltage is dropped because the voltage is energy carried per unit charge. So energy is dropped by crossing the resistor. So the total voltage dropped in the closed circuit, in the total circuit, when added, then it becomes the EMF supplied to the circuit. So when we will write it, EMF supplied to a circuit is the sum of all potentials across the resistors. Then this is called the definition of Kirchhoffs second law. Mean in a closed circuit, suppose this is a cell it is delivering voltage to these resistor, voltage V1, V2, EMF of the cell is this. So when V1, V2 is added, the answer will be EMF. Similarly, if the cell has internal resistance is always drawn in a dotted box. So this is internal resistance, this is EMF of the cell, first resistor, second resistor, suppose third resistor, so on, V1, V2, V3, and the voltage dropped here, suppose is VC, mean the voltage dropped across the cell, then the EMF of the cell will be equal to voltage dropped across the cell plus V1 plus V2, V3, and so on. And this is called Kirchhoffs' second law. Okay, now EMF E is equal to V1, V2, V3, and so on. But according to electric potential formula, electric potential is the work done per unit charge, mean it is equal to energy divided by charge. So this is EMF. Now the EMF can be written as the total energy per unit charge. V1 can be written as energy 1 divided by charge. E2 divided by charge, E3 divided by charge, and so on, because in series current remains same. So the charges are also same because I is equal to Q divided by T. So the total energy divided by charge, so 1 over charge is taken common, so it is E1, E2, E3, so on. Q cancel, so the total energy supplied to the circuit is the energy delivered dissipated across each resistor sum, and this is called law of conservation of energy. So Kirchhoff's second law is the law of conservation of energy. Now, the total EMF is V1, V2, V3, and so on. But according to Ohm's law, V is equal to IR. So the EMF total can be written as total current, total resistance, and V1, IR1, V2, IR2, V3, IR3, and so on. So in series, current remains same, resistance different, so different potentials. So IR, I common, R1, R2, R3, and so on cancelled. Hence, total resistance in series is calculated by this simple formula. So this is the derivation of the formula for the total resistance in series. So resistance total increases in series, decreases in parallel, but increases in series. Like when 3 resistors are connected, 5 ohm, 10 ohm, 15 ohm, then the total resistance R will be 5 plus 10 plus 15. So it's 30 ohm because R total is R1, R2, R3. This 30 even greater than 5, greater than 10, greater than 15. So the total resistance in series increases.